So let's look now at trigonometric identities. And what we're going to do is we're going to identify the fundamental trigonometric identities and then use those to simplify an expression. Now, in trigonometry, there are expressions that are equations that are true regardless of the angle, for any given angle. When this is the case, they are called identities. Identities are always true regardless of the value of the angle. Now, there actually is an infinite number of trigonometric identities, and we're going to spend this chapter proving a lot of these identities, but we need some basic identities first, our fundamental trigonometric identities. And these fundamental trigonometric identities come from our knowledge of a right triangle. So we're going to use this right triangle. We'll call this theta. And in relation to theta, the opposite side, we've done this before, is y. The adjacent will be the x value, and we're going to call the hypotenuse r. And since we know SOHCAHTOA, we can determine the basic trig ratios that come from this kind of triangle. So sine is opposite over hypotenuse, which would be y over r. Cos would be adjacent over hypotenuse, which is x over r. And tan is opposite over adjacent, which is x over y. Now, we've already looked at the reciprocal identities where we just flip those over. Y becomes the denominator in cosecant, and we get r over y, r over x for secant, and y over x for cosecant. Now, those just come from the basic identities. But let's look at any one of these identities, and I'm just going to look at the sine equation. Sine could also be solved for y. If we wanted to take sine theta equals y over r, we could solve this for y. Just multiply both sides by r, and we get an equation that y equals r sine theta. Now we can see the algebra. X would be r cos theta. And what this is going to allow us to do is to write our tangent identity as, instead of y over x, we're going to write it as tan theta is equal to r sine theta, the y value, over r cos theta. And lo and behold, the r's cancel out, and we have an expression, tan theta is sine theta over cos theta. Now, we can use that to find every one of our identities in terms of sines and cosines. For cosecant theta is r over, if we replace the y with r sine theta, we really just get 1 over sine theta, which we already knew. So cosecant is 1 over sine theta. We could say that secant theta is r over r cos theta, which is 1 over cos theta. And cotangent is the reciprocal of tangent. So we just flip these over, and we get cos theta over sine theta. And the important thing to notice here is that all of our trig identities can be written in terms of sines and cosines. Now, that's going to be very useful as we do more identities. But we're also going to use our knowledge of Pythagoras to find the other fundamental identities. And remember, Pythagoras' theorem tells us that a squared plus b squared is equal to c squared. Now, if we consider our triangle is x, y, and r, we can replace the a, b, and c in Pythagoras with x, y, and r. So really this becomes x squared plus y squared equals r squared. But remember, we found values for x and y. X was the same as r cos theta, so we'd have to square that, plus the y value is r sine theta. And of course, we're going to square that, and that's equal to r squared. Well, we can go one step further and square everything. We get r squared cos squared theta plus r squared sine squared theta. is equal to r squared. And if we notice that r squared is common in all three terms, we can divide everything by r squared. We have one of the most fundamental trigonometric identities. Cos squared theta plus sine squared theta is equal to 1. And there is one of our fundamental identities that we're going to use repeatedly through this course. Now we're going to use that identity to prove other identities. So if we take our cos squared plus sine squared theta is equal to 1, and if we were to take this and divide everything by cos squared theta, remember for an equation, as long as we do the same to both sides of the equation, it doesn't change the equation. What this is going to do is it's going to give us another identity. Cos squared divided by cos squared is 1 plus, well, we already said that sine theta over cos theta is tan theta. So sine squared theta over cos squared theta is tan squared theta. And that's equal to, well, 1 over cosine theta was secant. So this is secant squared theta. There's another fundamental trig identity. And if we did this exercise one more time, let's start with our cos squared theta plus sine squared theta is equal to 1. And this time, instead of dividing everything by cos squared theta, let's divide everything by sine squared theta. We'll get the third Pythagorean identity, squared identity. So divide everything by sine squared theta, and we're going to get cos squared over sine squared will become cotangent squared theta, plus sine squared theta over sine squared theta is 1, is equal to, and 1 over sine squared theta would become cosecant squared theta. And that gives us our three Pythagorean identities. Three values that have squares in them that are our fundamental trigonometric identities. And we're going to take these three Pythagorean identities and combine them with the identities that we already know. And here are the fundamental identities that we're going to use to solve and simplify trig functions and equations. Now, the good thing about these is you do not have to memorize them. We have to know how to use them. And that's what we're going to look at. How would we use these identities to simplify? Well, these are identities, but we also have what are called corollary identities, a statement that follows from the previous statement. What that really means is if we had sine squared theta plus cos squared theta equals to 1, and if we wanted to manipulate it to solve for just cos squared theta, we could actually do algebra to move things around and find a corollary. Cos squared theta is really just 1 minus sine squared theta. Just solving that for cos squared theta. Same thing can be said if you want to find sine squared theta. Just move the cos over and we get 1 minus cos squared theta. So take a second to see if you can figure out the corollary identities for each of the other two Pythagorean trigonometric functions. So there they are, just manipulating those original identities to solve for whatever we want. What we do have to be careful about is the positives and negatives when you are finding those corollary identities. So that tells us that the original three identities actually give us 9 potential identities when we consider the corollaries. So how are we going to use these identities? And when you're simplifying trig identities, there's certain techniques that we use all the time. There's not just one particular way to solve an identity. We're going to use techniques. And we're going to look at some of the strategies to simplify a trigonometric expression. And the examples we're going to do here are going to show you the most common types of strategies. So let's imagine our identity was something like this. Cosine theta plus sine theta over cos theta. We have an identity plus a fraction identity. And we want to combine them together. And we do this all the time of creating a common denominator. So take the value that's not a fraction, and remember, it's over 1, and we want to create a common denominator between these two. Well, the common denominator will obviously be cos theta. The second fraction we don't have to do anything with. And the first fraction, we multiply top and bottom by cos theta. Now, if there was a cos theta, that means we now have cos squared theta in the numerator. And if we were simplifying this, we would get cos squared theta plus sine theta all over cos theta. And that gives us a common denominator and a single fraction. So we're going to use that strategy a lot, creating a common fraction, combining things together into a single fraction. Well, what if we have one of the corollaries, 1 minus cos squared theta, or secant squared theta minus tan theta? What we have to recognize is this is actually a difference of squares. And remember, difference of squares, if we have x squared minus y squared, we can factor that as x minus y, x plus y. So 1 minus cos squared theta could actually be factored as 1 minus cos theta multiplied by 1 plus cos theta. It's really just a difference of squares. And the same can be said for secant squared theta and tan squared. This is really just secant theta plus tan theta. Remember, difference of squares, it doesn't matter which one comes first. Secant theta minus tan theta. Just a difference of squares. Well, what if we have tans and secants? And one of the most important strategies we're going to use is to take everything and switch it to sines and cosines. So tan and secant, we want to switch everything to sines and cosines. What we have to remember is the tangent is the numerator and the secant is the denominator. So we're going to create a fraction using fractions. Tan theta, if you look back, tan theta is actually the same as sine theta over cos theta, and secant is the same as 1 over cos theta. Now, it might look pretty ugly right now, but what we're going to do is we're going to simplify this. And remember, when we divide a fraction by a fraction, it's the same as multiplying by the reciprocal. So sine theta over cos theta multiplied by the reciprocal of the denominator, cos theta over 1. And this is often what we want to do, get a numerator and denominator the same. If it's all multiplication, they can cancel each other out, and we're just left with sine theta. So changing everything to sine and cosine, a very, very powerful tool when we are simplifying a trig identity. Well, there's one last common one, and it's multiplying by the conjugate. And if you remember, conjugates are really just the factors in a difference of squares. Conjugate pairs, x minus y and x plus y, those are a conjugate pair. So if we have 1 minus sine theta, whether it's numerator or denominator, we're often going to use the strategy of multiplying the fraction, and remember, as long as we do the same to the numerator and denominator, it doesn't change it, by the conjugate, 1 over sine theta. And as long as we do the same to the top and the bottom, it doesn't change the fraction. Now I'm just going to put brackets around this because now our numerator will be 1 plus sine theta, and the denominator, when we have that conjugate pair, well, remember, the difference of squares is just x squared plus y squared. So our denominator becomes 1 minus sine squared theta. Now that should ring some bells. 1 minus sine squared theta is actually an identity. And that identity that it becomes is 1 plus sine theta, numerator stays the same, all over cos squared theta. So that's the power of the conjugate. We can actually multiply by the conjugate and get down to a single identity. Now these properties that we use are the strategies that are going to be useful when we start simplifying trig identities. And we're going to spend a lot of time in class simplifying both equations and trig identities.